In this section, we are going to continue developing a few more tools so that we can use with a specific function in order to gather information about the function so that we can sketch its graph. So we are gathering tools, techniques that we will utilize in order to find info about a function and therefore be able to sketch an accurate graph. If you remember in the previous section, we started with a few tools. We learned how to use the first derivative to determine whether a function is increasing or decreasing in a specific interval. And we also developed the first derivative test that was telling us about given a function and its critical points, how do we tell whether the function has a local max or a local min at those critical points. Now we will see how to determine the concavity of a graph in a specific interval. Concavity is very important. Concavity, simply speaking, refers to the bending of the graph. In other words, if the function is concave up in an interval, that means that the function is somehow bending upwards. If it's concave down, it is bending in a downward manner. So this is just roughly speaking. In a while, we're going to go ahead and state that carefully here with formal definitions of what is truly the meaning of a function being concave up and what is truly the meaning of a function being concave down. But before we get to those definitions, we will try to do an exploration. Once we explore, for example, this given function right here, we will be able to see exactly the structure of the definition of concave up and concave down. Let's go back to this graph right here on the left. And I'm going to be moving from left to right, so from this left endpoint. If I move on the graph, let's say up to about halfway through the graph, it seems to me as if the graph is bending down. So it seems as if the graph in this region is concave down. If I now continue on to the other part, now the graph is bending upwards. So it seems as if the graph is concave up over there. So halfway through is where the change in concavity seems to happen. So because halfway through seems to generate a change in concavity, I'm going to go up to my graph, let's say over here, and I'm going to mark that point. Let me call that point point C. All right, so now let me draw a few tangent lines on this part of the function, so from A to C, and on the other part of the function as well. Here I have drawn the tangent lines on the two different segments of this graph. From A to C, I have them in blue, and from C to B, I have them in green. We're going to analyze those tangent lines. How are they changing as we move from A to C? Just look at them. Here, the tangent lines have a positive slope, but as I am moving towards C, the lines are becoming less and less steep. Right here, it is horizontal, and then they continue gaining some steepness, but now the slopes are going to be negative. So from positive slopes, we're going towards zero, and then onto negative slopes, and those tangent lines are going to start getting steeper. So in terms of the actual value of the slopes are actually getting smaller and smaller and smaller as x moves from A to C. That is really telling us pretty much that the first derivative, f prime of x, is actually decreasing from left to right. So I'm going to say over here that in this region, f prime of x is decreasing. Again, as we're moving from left to right. Now, on the other part, from C to B, still going from C, from left to B, that means towards the right. If you look at the tangent lines, the slopes are negative, but then they are actually increasing because this line over here is steeper than this one, and this one is steeper than this one. In fact, the one that I'm highlighting right now is horizontal. And then the lines are getting steeper and steeper and steeper with positive slopes. So then what I am seeing here is that the derivative is actually increasing from left to right. So I'm going to make a note of that. In this particular case, f prime of x is increasing. And if you remember, we said that this part of the graph seems to be concave down, and this one is concave up. And what we have noticed is that concave down relates to the first derivative being somehow the first derivative decreasing in that interval. And concave up relates to the first derivative increasing in that interval. And this is exactly what the definition is going to tell us. The definition of concavity says that suppose that f is differentiable in an open interval AB. Then, if it's differentiable, f is concave up in an interval AB if and only if f prime of x is increasing, and I'm going to say over here, from left to right. And we can see that again. Let me take you back to concave up, right there. Exactly the part of the graph with the green tangent lines. Notice how the slopes of the tangent lines are actually getting larger as x is moving from C to B. And then in the other case, f is concave down in the interval AB if and only if f prime of x is decreasing as we move from left to right. And this part over here is shown over here on this part right there. You can see that on this segment with the blue tangent lines, the slopes of the tangent lines are actually getting smaller and smaller and smaller as x moves from A all the way to C. So this is exactly the main definition of concavity. A function is concave up if the first derivative is increasing, and a function is concave down if the first derivative is decreasing within the specific interval AB. What I want to do now is to go ahead and sketch the first derivative of this graph. I am going to do that by noticing some key features of the tangent lines here. So over here, the tangent line is horizontal and horizontal right here. So I am going to denote those points by calling them M, and right here, this is going to be N, a dot there, and let's put a dot right there. Those values are going to transfer here, M and N, because this is where the first derivative is going to have x-intercepts. Let me even put here on the y-axis y prime to remind you that this is going to represent the graph of the first derivative of the graph above right here. I also want you to notice how the tangent lines from A to M have positive slopes, and then from M to C, they have negative slopes, and how those slopes are actually decreasing. So in order to denote that, we're going to have the graph coming down like this, passing through M, going under the x-axis, but then halfway through is when the tangent lines change direction. So all of a sudden now, they're getting less steep, still negative slope. then 0 at n, so it's going to, the graph of the derivative passes through the x-axis at n, and then the slopes become positive. So then the graph of the derivative is going to be above the x-axis. So trying to capture all that, we're going to have something like this. At C, which is going to be somewhere here, we're going to have a turning point, and then the graph continues up like that. And I'm just doing a rough sketch. Nobody says that it looks identical like this. So that will be my first derivative. And next, we're going to go ahead now and investigate the second derivative, because in order to find the intervals of concavity of a graph, we are going to be using the second derivative, not the first derivative. The first derivative is limited to local extrema. For concavity, we're going to be using the second derivative. So in the next discussion, we're going to now continue from y prime onto here, y double prime. Here, we're going to go ahead and sketch the second derivative. We can already see exactly what's going to happen. I'm going to draw a few tangent lines, but you already know that the first derivative is decreasing from A to C. You can see how the graph is going down. And then the first derivative as a graph is increasing. Look at those tangent lines. Now, as I draw tangent lines, think about it. Tangent lines on the first derivative graph are really telling you something about the second derivative. So these tangent lines are really representing the rate of change of the first derivative, which happens to be the second derivative. So we really notice that the tangent lines on the first derivative, hence the second derivative, it is actually increasing from left to right. They are increasing very steep negatively, and then they're getting less steep, still negative, and then at C, the tangent lines get horizontal. So the tangent line is horizontal at x equals C. That means that x equals C is very important for us. This is where the second derivative is going to cut through the x-axis. And then if we also notice that at x equals m, the tangent line has a negative slope. So let me position m somewhere here. And when we look at x equals n, the tangent line has a positive slope. So let me go ahead and also position n somewhere here. Then from negative slope means that the lines, the second derivative is going to be below the x-axis. Let's say something like this is going to cross through x equals c, and then it will transition upwards like that. Again, I am not trying to be super careful here. This is just a rough sketch. This is my second derivative. So look at this now. From A to C, we started with the portion of the graph that was concave down. That really told us that the first derivative is decreasing from left to right, from A to C, and this was the definition of what it means for a function to be concave down. And when we go to the second derivative, this is telling us over here that the second derivative is less than 0 from A to C. We can see that. We can see how the second derivative is below the x-axis. Then let me go back to the upper graph right here, from C to B. From C to B, the graph is concave up, which really meant that the first derivative is increasing, and that was part of the definition. Then when we go to the second derivative, we can see how now the graph is above the x-axis because the graph is increasing. Those tangent lines have positive slopes. So I feel that this is now giving us enough information to really establish the test for concavity. The test of concavity says that if f is twice differentiable, that means that you can find the first derivative and the second derivative in an open interval AB, then if we know that the second derivative is greater than 0 in AB. Let me take you over here. Look at this part over here. The second derivative is positive. This meant, going back to the very first graph, that this part of the graph was concave up. So a positive second derivative in some interval is telling us that the graph is concave up in that interval. I'm going to write that down. Then we will say f of x is concave up in the interval AB. And then the second part says that if the second derivative is less than 0 in an interval AB, so let me take you over here. Here is the second derivative, less than 0. Let me now go to the first graph over here, from A to C, where the second derivative is less than 0. Look at the graph, is concave down. So then, if the second derivative is less than 0, then f of x is concave down in that interval AB. And this again is the test that we're going to use to investigate the concavity of a graph. We are going to go ahead and we're going to look at the second derivative within a given interval, and we're going to find out what is the sign of the second derivative. If the second derivative is positive in that interval, the graph is concave up. And if the second derivative is negative in that interval, the graph is concave down. Let's go over a new concept, that of a point of inflection. What is a point of inflection? Let me take you back to the first graph. Notice from A to C, this part of the graph is concave down, and this part of the graph is concave up. Concavity changes exactly at x equals c. Well, because concavity changes at x equals c, this point right here, where the concavity changes, is called a point of inflection. It becomes a very important point. Something big happens. Concavity changes there. Let me even highlight it in red. So this point right here is called a point of inflection. And based on my drawing, the point of inflection happens exactly at x equals c. Now let's go ahead and state the definition formally. I already got us started. Suppose that f is continuous at c, comma, f of c. This is the point of inflection. In other words, I am calling this point, or I am giving this point coordinates c, comma, f of c, the point of inflection. If f is continuous, continuity is important at the point of inflection. If f is continuous there, then c, comma, f of c is an inflection point for f. But it must be if and only if we will say concavity changes at c, comma, f of c. I'm going to go ahead and write that down. If and only if concavity changes at c, comma, f of c. In other words, we may go, if I have over here my point C, and let's say the graph is concave up on the left and then concave down on the right, then x equals c is where the point of inflection will occur. Or let's say if this is c, and on the left of c the graph is concave down, and on the right of c the graph is concave up, then again I know that at x equals c my graph is going to have a point of inflection. But this is under the assumption that c is part of the domain of the function is continuous, And the most important condition, concavity changes around x equals c. Now that we know what inflection points are, the next question is, how do we find them? Given a function f of x, how do I find specifically the values of x where concavity is going to change? If you look at the title of this theorem, it is test for inflection points. So this is telling us that there is a tool, there is a way for us to be able to figure out if at a particular value of x, the concavity of the graph is going to change there. Now, before we do that, let's go ahead and try to figure out how to do that. What's going to happen? What really happens at x equals c? C right here. If you remember, in the first graph, it was at x equals c where the concavity changed. We went from concave down and then concave up. When we now go to the first derivative, it is at x equals c where the first derivative turns around. In fact, you can see there that the slope of the tangent line is going to be 0. The tangent line is horizontal at x equals c. Again, x equals c is that turning point of the original function. Then transitioning onto the second derivative, well, if the tangent line is horizontal at x equals c, that means that this is going to be an x-intercept for the second derivative. Simply speaking, the second derivative at c is going to be 0. Let me actually mark that down. I see right here that f double prime of c is equal to 0. This is then a huge realization for us. This is practically hinting that an inflection point happens exactly at a value of x where the second derivative is equal to 0. That means that if we're trying to find those inflection points, we are going to be looking at the second derivative, particularly where the second derivative is equal to 0. And that's going to be over here, part of that test for inflection points, or that search for inflection points. Now, I want to make a note then that inflection points do not only happen where the second derivative is equal to 0. If we say that the second derivative at a value of x is equal to 0, we are assuming that the first derivative exists. In other words, we are assuming that the function is differentiable at the value of x where the inflection point takes place. However, the graph doesn't have to be differentiable at an x in order to have a point of inflection. For example, I can have a function like this, and then moving up in that direction really quickly. Imagine. This is now my c right here. And if you notice, exactly at this point right here, the concavity changes on either side of c. On the left of c, the graph is concave down, and on the right of c, the graph is concave up. However, there is a sharp corner there. So then the function is not differentiable. Now, it is continuous, right? This is a nice continuous graph, but because of the sharp corner, it's not differentiable at c. However, concavity changes there. In other words, at x equals c, the function is going to have a point of inflection, even though it is not differentiable there. So then I think that we're ready for theorem 2 to be able to state it nicely and to finish it up. The theorem says, suppose that f is continuous in AB and c is in AB. So c is a point in this interval AB. If the second derivative at c is equal to 0. In other words, Let me take you here, something like this c on the left. Or if the second derivative at c does not exist, like right here, right? This is supposed to be the graph of f. Well, since the graph of f has a sharp corner at c, the first derivative doesn't exist. So therefore, the second derivative doesn't exist as well. So if the second derivative at c does not exist, and if, though, concavity changes around c, and if concavity changes around c, then f of x has a point of inflection. It has a point of inflection at c, comma, f of c. So that's what we want. In order to locate the points of inflection, we're going to find the second derivative. We're going to see where the second derivative is equal to 0 and where the second derivative is undefined. When we find those x values, then we're going to check the concavity around them. And if the concavity changes around those x values, then that's where we know that f of x is going to have points of inflection. Now on to the final discussion. If you remember in the last section, we developed the first derivative test. The first derivative test was to identify local maximum and local minimum values. So it was exactly to figure out where the function has local extrema, but local extrema. Now that we have explored the second derivative, we can also use the second derivative to find local extrema, believe it or not. The second derivative so far has been used for concavity, for points of inflection, but we can also use the second derivative to investigate whether a function has a local maximum or a local minimum at a critical point. We can do that. Let's look at the graph above. We have critical points at m and n. So these are the two critical points of this function f of x. Then, when we transition to the first derivative at m and n, the first derivative has its x-intercepts there. But then when we transition to the second derivative, see what happens. At m, the second derivative is negative. This is where we had a local maximum. Local maximum at m, second derivative is negative. And over here at n, local minimum. Let's look at the second derivative. The second derivative is above the x-axis, so it's positive. Then we're going to have the second derivative test. This is what the second derivative test says. We are going to be given a function f of x. We're going to go ahead and we're going to find the critical points right here. We're going to do that in the same way that we learned how to do that in the previous section. Once we find the critical points, we will not proceed with the first derivative test. We're going to continue and we're going to take the second derivative of the function. We're going to find f double prime right here. Well, obviously, if it exists. So then, when we find f double prime, we will evaluate the second derivative at x equals c. We will see what is f double prime of c. If f double prime of c is bigger than 0, if you get a positive number when you plug in c into the second derivative, then that means that the function has a local minimum at c. Let me write that down. Then f of x has a local minimum at x equals c. And you can see it right here. For if the second derivative is positive, at n, let me go back all the way to the beginning. At n, we had a local minimum. So practically it's the opposite that you have. A positive second derivative means a local minimum. Then if the second derivative is less than 0, if it's negative, then f of x has a local maximum. A local maximum at x equals c. And if the second derivative at c happens to be equal to 0, then the test is inconclusive. Then the test, in other words, the second derivative test, is inconclusive. You know, that doesn't mean anything. Inconclusive means that you cannot draw any conclusions. In other words, the function f of x may or may not have a local maximum. It may have a local maximum or it may not have a local maximum. So f of x may or may not have a local extrema, let's say, at x equals c. So then, if the test, the second derivative test, is inconclusive, what do? You're going to go back to the first derivative test, and you're going to see whether the first derivative changes sign around c. Are we going from increasing to decreasing, or are we going from decreasing to increasing? So if the second derivative gives you an inconclusive scenario, then you're going to go back to the first derivative, and the first derivative will take care of everything. Now, the second derivative test seems nice as long as it is easy to compute the second derivative of the function. For some functions, it is super easy. It is a no-brainer to find the second derivative. But there are sometimes some functions, actually the majority of functions, where it becomes so tedious to find the second derivative. So if you have situations like this, it may just be better not to bother with the second derivative test, to just go ahead and do the first derivative test, if all that you want is to figure out whether your function has local extrema or not. So second derivative test, I think, is ideal as long as the second derivative is fairly doable.